You guys rank completing the square as the hardest non-calculator topic in all of GCSE maths. So I animated a quick 3-minute video to help you guys understand it.
Today, we are going to master a powerful technique called completing the square. By the end of this lesson, you will be able to explain the geometric why behind this method and use it to find the turning point, or vertex, of any quadratic. Let's start with this quadratic expression. Our goal is to find its turning point, without just memorizing a formula. To understand the why, let's look at just the first two terms, x squared plus 6x. Imagine these terms as areas. X squared is literally a square with side length x. 6x is a rectangle with one side of length x and the other of length 6. To find the turning point, we want to turn this shape into a perfect square. If we take our rectangle with width 6 and split it in half, we get two smaller rectangles, each with a width of 3. Now, let's place one rectangle on the right side of our square and the other along the bottom. Notice that we almost have one large square, but there is a piece missing in the corner. What is the area of that missing piece? Since the sides of the gap are both 3, the area needed to complete the square is 3 times 3, which is 9. By adding this 9, we've created a perfect square with side lengths of x plus 3. Now that we understand the geometry, let's look at the algebra. We can't just add 9 to an equation whenever we want. That would change the value of the expression. We start with our original equation. To keep the equation balanced, if we add 9 to complete the square, we must immediately subtract 9 as well. This is like adding 0, which is mathematically legal. Remember our geometric square? The part in parentheses, x squared plus 6x plus 9, is exactly the same as the quantity x plus 3 squared. Finally, we combine the constant numbers outside. -9 plus 5 gives us -4. This form of the equation is called vertex form, or turning point form. Now, let's use this to find the turning point. Think about the behavior of this expression. The term x plus 3 squared is a squared number. Since any real number squared is never negative, the smallest possible value this part can be is 0. This minimum value happens when the inside of the bracket is 0. That occurs when x equals -3. If we plug -3 into our equation, the squared part vanishes, and we are left with y equals -4. So, the lowest point on the graph, the turning point, is at the coordinates -3, -4. Let's see it on a graph to confirm. As you can see, the parabola curves exactly at the point we calculated. To summarize, we divide the coefficient of x by 2 to see how to split our rectangles. We square that number to find the missing corner. Then, we adjust the constant to find our turning point. You now know not just the formula, but the actual geometry of why completing the square works. You've turned an abstract algebraic trick into a concrete visual tool.